All right. Hey everyone, welcome back to Chemistry 3-4 ATAR Notes lectures. This one today is going to be our September lecture, which is pretty exciting because it is our penultimate last lecture before we move sort of into that exam phase. And for us, it's really our last lecture to you guys for Chemistry 3-4 for the year. So if you've been following along throughout the year, I've been running sort of each of these lectures, and we started off with a bit of head start in January where we covered our fuels and a little bit of redox, and then we moved into our equilibria and covered off electrolysis in our sort of autumn, sort of April lectures. Move into June, July, and we did our June, July, and we covered our OChem, our organic chem. And then today we're going to finish off with a bit of spectroscopy, and given exams are right around the corner, you've got about 2 or 3 weeks until your exam. We're going to finish it off with a little bit of sort of exam technique and some tough exam questions, just so that we can ensure we've covered everything leading into the end of the year, which is pretty exciting. So looking at this lecture, we're going to cover for the 2 hours a couple of different things. Just as some starting off points, a big welcome from us at ATAR Notes to all of you here today. Those of you watching the premiere, which is I'll be at and answering any of your questions during, or those of you watching the recording a little bit later on, welcome to all of you, and welcome to sort of ATAR Notes, especially if this is your first time getting around these lectures. ATAR Notes has been delivering free lectures for a very long time, I think since about 2007. Which is a very long time ago for a lot of you. You're very, very young at that point in time. But since 2007, they've been delivering these lectures, and they've been delivering them for free, and they continue to do it to today. And they have a whole bunch of different resources as well, which is pretty exciting. You can find study notes, these lectures, discussions, videos, all sorts of free content online. They also now have sort of their paid resources as well, where they sort of can segregate the two different things, and they've got their ATAR Notes Plus. So ATAR Notes Plus was new in 2024, at the start of 2024, end of 2023. It now has an AI answer bot. It's got all of your study guides online. It's got all of your topic tests online. It's got all of the NEEP content online, since NEEP is now part of ATAR Notes the last couple of years. It's got your text guides for English, because English is technically the most important subject, even though we all don't like saying that. And it has a lot of other resources in terms of flashcards and other question banks and so forth. So definitely something worth getting around. We also have our tutoring service, TuteSmart, which is where I sort of come into this and where most of the lecturers come into it. We all work through TuteSmart and sort of delineate off to the side and do some ATAR Notes work as well. And you're welcome to check out all of that. There's always, during these lecture series, there's always a lecture highlighting, ATAR Notes versus TuteSmart versus our ATAR Notes Plus, and you're welcome to attend those lectures and get a bit of an idea of what's going on with the three and whether there's some options for you, especially if you're in Year 11 and you're watching this and this is your Year 11 topic, your Unit 3, 4 and Year 11, and you're looking into Year 12 and you're like, how am I going to improve on my marks, etc. These are always great options. So as I said, welcome. This is our sort of our spring, September lecture series. Obviously, this is a new study design, but just some other housekeeping things. Feel free to use the chat. As you can see, when you're at the premiere, you're welcome to use the chat. I will be there. I will answer any questions that you have. Please keep the questions chemistry related. The slides will be accessed below. The recording will be available after the premiere on the same link. However, this is only available for about a week. So really important, these are only available for about 1 week, and then you will need to access it through ATAR Notes Plus. So if you've got friends who can't make it to the live premiere, make sure they get around it in the first week. And a bit about who I am. I've been at ATAR Notes now for about 6 years. I've been around for a very long time. I did chemistry way back in 2018 with about a 44, 45. I actually forget off the top of my head what my mark is now. But ended up tutoring Chemistry 3-4 from pretty much first year at uni. And now what I'm doing is I'm at uni. I'm in my final year as a medical student at Monash University. And that's who I am. So lecture plan today, this is probably the important one. What are we actually going to do during our lecture today? So we've got a couple of different things that we're going to do. So what we've got is our analytical chem block, which is going to go for about 70 minutes. Then we've got our exam technique block, which will go for about 20 minutes. And then we've got our tough exam questions at the end. So what I've done is I've gone through VCAR papers and I've found sort of the more tougher exam questions that you can go through, and I've put those in together. I actually haven't updated this slide for some reason. I do apologize. This is not meant to say electrolysis, OChem, and exam approach, because we are going to actually go through different things today, which is analytical chem, exam technique, and tough exam questions. I always put these in my slides, but have a look at the study design. It's really important that you understand the study design for these topics. We're not going to go through experimental design. And as part of analytical chem, there's a lot of medicinal chem stuff. We're just going to touch on that very briefly. We're not going to go through that in super duper detail. So let's get started on our analytical chem. Now, I do advise for this, really important, have up your study design on the side. It's always really useful to have that up so you can always come back to it. And I think it's quite a useful thing to have. So I will always be flicking between the two. So when needed, I will be doing that. So let's have a look at this here. So what are we going to be looking at today? So what we're going to be looking at is we're going to be looking at a little bit of analytical chem in terms of how do we actually approach our analytical chem. So really important to understand that with analytical chem, we're approaching things in sort of a three-pronged approach is how I like to think about it. So this three-pronged approach bases itself around separation, identification, and then quantifying or quantification. So these are your three sort of phases. Now, what's really important is that separation and quantification, you've actually already done before. You've covered all of it. You've covered HPLC and chromatography in Unit 1-2. You've covered volumetric analysis, so acid-base volumetric analysis in Unit 1-2. And you've covered redox as part of your Unit 3, Area Study 2, Area Study 1, technically part of both. So you've actually already covered most of this. However, we are going to go back through, and when you do this topic, and I'm assuming most of you have, given that we're running this sort of term 3 holidays, you should have already gone through this stuff, but most schools will go back through chromatography and acid base, especially given titrations and chromatography, especially HPLC, it's actually quite high yield. If you've started doing practice exams and you've looked through the last couple of years, you will have noted there's actually a lot of chromatography and there's a lot of volumetric analysis. It just seems to be something that comes up a lot and something that they seem to put a lot of effort into. And so if you have found that, you'll understand why we go through these topics again, because they are pretty high yield. So let's talk about analytical chemistry, and let's talk about straight after that paper chromatography. Super low yield, has come up a couple of times in the past. The only reason we discuss it still. So paper chromatography, there are 2 points to paper chromatography. There is one, this idea behind the getting your standards, and then two, there is this idea behind making sure that you understand your RF factors. These two features are pretty straightforward. Paper chromatography really shouldn't be challenging you too much. It is something that you just need to know the basics of. So what comes up in paper chromatography is this two-pronged idea. So the first idea is that if you place a sample at an origin and you dip it in a solvent and you allow that solvent to drag your samples up the paper, you should get the components of that sample breaking up. Now, they will move along to a point, and essentially then it'll sort of dry out and it'll stop. What's really important is that you've got no idea what that is. So the only way that you can identify what that is if you have a standard. Now, it is chromatography, and we have talked about chromatography being the idea of separation. So you will separate the components. That is fine. But chromatography can also, or paper chromatography can also sort of double-handedly be used as a bit of a quantifying or a bit of identifying, really. And you can identify what actually are the components, because you can look at it and say, all right, where am I moving to compared to my standard? So if you have this unknown fruit sample and then you have a glucose sample and a fructose sample, you can identify that this unknown fruit sample has both because they are both at the same level of going up. So then from there, you can also do some quantifying in terms of you can do some maths. And what's really important is that this maths is very simple. You're essentially taking the solvent front and you're going, all right, where is my solvent in comparison to that solvent front? So the distance, the component from the origin versus the distance of the solvent front from the origin. You do some division, you find out a factor. Now, really important, this factor should always be less than 1. If it is not less than 1, you've done your maths wrong, because this should never be in front of the solvent front. If this is in front of the solvent front, then this is not your solvent front. Your solvent front should always be ahead of it. It can be equal with it. So then you get an answer of 0.99, or technically you get an answer of 1, very unlikely. But you should never ever find this to be more than 1. If you get more than 1, you've made a mistake. You need to go back. All right. Then we get into HPLC. So HPLC is actually where you're going to get your marks in this. HPLC does actually quite commonly come up. So high-powered liquid chromatography is very, very sensitive. It's a technique that can detect components present concentration as low as 1 parts per billion. Very cool. What it does is it separates things. And you can understand how many components you have. So what you do is very simply, you get a column and you pack it really, really tightly with something. So usually it's like it's a fine sort of sandy-like material, but it's super duper fine, like a sugar sort of type material, and you compact it really tightly. When you compact it really tightly, you then add your sample to the top of it and you push it through to the bottom. Now, the reason you have to push it through the bottom is you've packed it so tightly, it's not going to get through if there's no pressure. If you're not pushing it through, nothing's going to get through. And so what you actually have to do in this case is you have to go, all right, this is never going to get through. I need to start forcing it through. And as you force it through, things start to separate because they move through at different rates. Now, what is this idea of moving through different rates? Well, there is a concept of mobile phase and stationary phase that makes things a little bit easier to understand. So you have your mobile phase and you have your stationary phase. Now, your mobile phase is your liquid or gas that you're pushing through. Your stationary phase is the solid high surface area that's in there. You can also technically use a liquid, but it's not as common. You'll usually use a high surface area solid. That is usually that crushed up minerals, sandy-like material that's really fine and allows you to push everything through. And what's really important is the mobile phase will carry the sample through. So the sample may just purely be a liquid, so it's the mobile phase. Sometimes your sample is actually a solid, so you need to dissolve it into a mobile phase, which is just like your solvent, and then you push it through. And then your stationary phase is what separates the components. Now, there's some really important wording with this that you need to understand. And that is this idea that when you're moving through the stationary phase and you're moving through the mobile, and your mobile phase is moving through the stationary phase, it's really important to understand that the reason things separate is because of this concept of adsorbing and desorbing. Now, when I say adsorbing, I'm not saying absorbing, I'm saying adsorbing. So adsorbing. I've got terrible handwriting when it comes to drawing on a Mac, so do please excuse it. But it's adsorbing, AD, and then desorbing. Now, what does that mean? It means as the mobile phase moves through, the sample will adsorb itself to the stationary phase. So think of it as you've got, your fine little bit of material here. It comes down. This is your mobile phase, and it sort of adsorbs and it rolls around, and then it comes off. So think about like water running over a rock. Now, what happens is the different level of adsorbing. So adsorbing is not, so I should probably explain. Absorbing, think of absorbing like a sponge, and you put sponge in water and it sucks all the water in. Adsorbing is not that. Adsorbing is like putting the sponge there and the water sort of hits it and then rolls around it and goes around it like that rock. It's not actually absorbing the water into the rock, it's going around it. That is adsorbing. So in this case here, adsorbing is where it goes around it. Now, if you have a stronger ability to adsorb the mobile phase, if you're the little rock and you really like this mobile phase and so you try and stick it to you as long as you can, it's going to take a lot longer for that sample to get through. Now, if you hate the mobile phase and you are just like opposites to it, you'll push that mobile phase off as quickly as you can. So that mobile phase will be very quick in going around. It'll have a very brief adsorption and a very quick desorption, desorption being pushing it off. If you have that scenario, your mobile phase is going to get through a lot quicker. Now, the different components of a sample will all have different adsorbing and desorbing levels, and therefore that is why you get this separation. Now, how do we know or predict how things are going to go through? Well, it depends on your polarity, because polarity is going to determine your attractiveness. So if a mobile phase, so in this scenario, we have a mobile phase and it is polar, and we have a stationary phase that's non-polar. Generally, we'll always have opposites. So we've got a mobile phase that's polar and a stationary phase that's non-polar. What's going to happen? Well, the polar solvent is going to flow through a lot quicker, because if you've got a polar solvent, it's going to attach to that mobile phase, and the stationary phase is not going to want a bar of it. It's going to be pushing it off and it's going to move through really quick. But if you've got a non-polar solvent, it will flow through a lot slower because it's going to be really attracted to the stationary phase, and so it's going to adsorb a lot and desorb a lot slower, and so its movement through is going to be a lot slower. Obviously, if you've got the opposite, it's going to be the opposite. So HPLC, really importantly, can separate things, but it can also measure concentrations. So it can also do a bit of quantifying, because as you can see here, you get this is what a chromatogram looks like. So this is a chromatogram for a HPLC. You've got minutes going this way. And so essentially you've put a sample through at 0, and then you get this sample coming out at different points. So you get 1 point here, 1 point here, and 1 point here. So what you can tell from that is that your sample had 3 distinct components in it. So you've separated the components. If you have taken out this component and then removed it and then taken out this sample, you've actually started to separate your different components from your sample. So you've got 3 distinct components, and that's really important. Your 3 distinct components have all got different concentrations or different amounts. How do I know that? Because of this intensity. Now, the intensity doesn't generally have a scale. You can find that usually sometimes they'll call this 100%. Why? Because they use that as its own scale. They say, oh, look, the most intense one is 100%, and then everything is based off it. But essentially what this is saying is that the most amount of, or the largest percentage of this sample is made up of whatever is this component at 4 minutes and 45 seconds. The next most prominent component is probably this one here, and then this one here. Now, really important, it's the area under the sample. It's the area under. So you'd have to do some very complex maths here, but we don't expect that of you. Generally, what we say is that the sample is just, we treat the one that's the highest as the one with the strongest and the most, and then scaling down from there. So looking at that there, what's also really important to understand is that you can then do standards. Just like our paper chromatography, you can do standards. And when you do these standards, if you put something that you know through the exact same column and it flows through and it comes out at a certain time, if you put a sample of unknown components in and something comes out at that exact same time that the one that you knew came out, you generally say that's the same thing. So if you're putting through the same thing, whatever it is, if you're putting through propane and you put through multiple propane types through, or multiple propane samples through, and all of those samples are different concentrations, doesn't matter, they're all going to come out at the same time. The only thing that will change is this intensity. So we have a VCAR practice question from this. I think it's from about 2014. Don't remember off the top of my head. Nonetheless, you've got a following chromatogram was produced for 0.1 micrograms of decane. It was passed through a gas chromatography column. So don't worry about the gas chromatography. It's the same thing as HPLC. And this is what you've got. And then it says you've got 0.2 micrograms of decane. So you've doubled your decane and we passed it through the exact same column under identical conditions. It is best represented by 1. So if you want to have a go at this, please pause and have a go. 3, 2, 1. Hopefully you're back and you had a go. So Maybe what I mentioned before with that propane example. Propane will always be the same. So you're not going to get a change in your propane. Thus, in this case, we've still got decan. We've got decan and we've got decan. So having decan and decan, we're going to have it at 10. It's going to stay at 10. So A and B are wrong. Straight off the bat, I'm comfortable A and B are wrong because they reduce their retention time. That's not possible. You're using the same sample in the same conditions, but you've got more of it. So that tells me that the intensity should change, and doubling it, it really should double the intensity. So it should go up to about 20,000 because this one went up to about 10,000. So if I look at this here, this one's still at 10,000. This one's at 20,000. Your answer here is C. It's the best way to go through this. So that is chromatography. There is more to chromatography. You can make calibration curves and so forth. Those are probably the next steps on. We're not going to go through that today, given our sort of time restraints. Let's go on to spectroscopy. So now that we've separated, we now need to identify what we've got. And the best way to identify what we've got is to use spectroscopy. Now, I'm going to preface this by saying spectroscopy is difficult. That's really important to understand. Spectroscopy is difficult. Now, why is spectroscopy difficult? It's because it's brand new and because it's quite hard to sort of get your head around what's going on. Now, I'm hoping at this point in time, you've all sort of been through it in school and you all feel a little bit comfortable with it. So what we're going to do today is give a very brief overview of the main points that I think you need to know for the exam. I'm not going to go through these in super duper detail and go through, hey, this is exactly how you do this is exactly how you do that. I'm going to go through the points that I think are relevant to the exam. What are you actually trying to get out of this? So, really important, 3 types of spectroscopy, and the 3 types of spectroscopy need to be used together. Please do not use them separately. You need to use them together. One goes with the other. They are not there to be used separately. They are there to be used as one. So please use them as one. And I think that is really important. I feel like there are times where students are too set on using one over the other. That is not how that works. You need to use them all at once. And that's really, really important. You need to look at your mass and then use the information you have from your mass to use in your IR. And then the information you have in your mass and your IR to help you with your NMR. So please use it like that. It's a really important skill. You need to be using them all together. So, looking at this, we've got molecular mass found from your mass spec, your functional groups found from your IR spec, and your connectedness from your NMR. So, let's start with mass spec. Mass spec is by far the most straightforward. Why? Because you are always going to take your most basic information from your mass spec, and that is going to be your molar mass, which is going to be here. Reality is you've probably got some isotopes in here. That's why you've got a point at 60. But your most common one, this is your base peak. It's also your parent molecular ion peak. It's at 59. This molecule is going to have a molar mass of 59. So that is the information you want from mass spec. You can then start to look at, all right, there's a peak here. There's a peak here. There's also sort of a bit of a peak here. All right, what's actually going on here that is making me change? What are these different fragments that I'm looking at? That can assist you a little bit, but the most high yield piece of information you can take from this mass spec is the molecular ion peak. I don't even think the base peak is that important. The molecular ion peak is by far the most important piece of information you're going to get from mass spec. It's the one thing you just have to get. So let's just quickly talk about the method, because mass spec is the one where you actually find they're pretty onto it. They actually want you to be able to discuss the method a little bit. When I say discuss the method, they don't want you to be like, oh, you put the sample in this part of the machine and the machine then turns on and then you bombard it with electrons, yada, yada, yada. They don't want that level of detail. They know you know that it's bombarding with electrons, and you need to be able to say that in an exam, that mass spec is all about bombardment with electrons. It's important you know how to do that. So you do need to be able to mention that. But what do they actually want? Well, they actually want you to go through it and say, all right, if I bombard XYZ, or in this case here, what are we working with? We're working with propanoic acid. So this is propanoic acid. I'm bombarding propanoic acid with electrons, and I'm going to fragment it with the CH3 coming off what it's actually going to look like. And they expect you to be able to draw something like this or something like this. So it's really important. There's two aspects, the ionization and the fragmentation. The ionization is the bombardment with electrons. This is the bombarding electron. It takes an electron with it. Therefore, you need to put the brackets around it with the positive. It still stays as a gas, that doesn't change, but you now have this positive symbol because this has been bombarded and it's lost an electron. The losing of an electron makes this molecule unstable. Now, being unstable doesn't necessarily mean it's going to fragment. It may fragment, it may not. That's why you get your parent molecular ion peak, because some of them don't fragment and they just pick up this cation going through that hasn't fragmented. But some will. And when those ones that do fragment, you get two different things. You get a free radical, which is delineated by this dot. And it's really important when you are drawing this out, you do the dot. You don't just go CH3, apologies for my terrible handwriting, and then just do like a dot like that. That's not good enough. It needs to be like this. It needs to be very obvious. Make it big, make it obvious, and use pen. So you are going to be doing CH3 like that as a free radical. And then the other fragment, which in this case here is the CH2COOH, that is positive. Now, which one am I going to make positive? Which one am I going to make the free radical? Unless the question tells you, it's either one of them, because it's completely random which one becomes the free radical and which one becomes the cation. There are most likely, and there definitely are, because I know some knowledge and some aspects of molecules that changes which one ends up with the free radical and which one ends up with the cation. However, at VCE level, you don't need to know that. You just need to know that one of them will be a free radical and one of them will be a cation. So one needs the positive and one needs the free radical. And it's really important you know how to draw this out with your brackets and your positive and your free radical. Why is that important? Because they will ask you a question and they will say, oh, like, you understand that the molecule is this. So you understand the molecule is propanoic acid. And you get given a mass spec, and on that mass spec, they give you a spot. Actually, I'll go to the next slide and I'll show you what I mean. So you've got this fragmenting. That's your molecular ion peak. And then you've got this fragment here. So this fragment comes up down here at 15. Now, a very common exam question is, you have a fragment at a MZ ratio of 15. What is that fragment? And it's a 1 mark question. You've got one line. Now, if you write, oh, wrong one. Give me a second. Sorry. If you write CH3 on your line, and remember, they are asking you, what is the fragment? That is wrong. Why is that wrong? Because this is the fragment. This is the fragment. Just writing CH3 does not delineate whether it is a free radical or a cation. You must show that it is a cation. Show that you know what you're doing. Show the examiner you are on top of this topic and put the positive cation there, please. So, really important, you need to do that. And then this here's a really good diagram. I made this a couple of years ago and I use it everywhere. I think just being able to identify what are these fragments, this is a great mass spec. So if you have time, you can go back and just grab some random mass specs and ones that have a name, so like ethanoic acid, and then literally go through and go, all right, what are my fragments that I can see there? And literally draw them out and you can see exactly what's going on. Now notice with each of these, positive, positive, positive. I put a little positive next to them just to remind me that I'm working with the cation here, not the free radical. Really, really important. Now, the other really high yield aspect of mass spec. So the mass spec, you've got sort of 3 main high yield aspects. You've got this idea of what is the parent molecular ion peak. That's really important. Sort of base peak is also high yield, but not as important. Parent molecular ion peak, which is the molar mass of your unknown sample. You have the positive versus free radical, the cation versus free radical, and how to draw that. That's also super duper important. And then your third really high yield aspect that I think a lot of students don't go through enough is isotopes. So remembering, isotopes are common. You did last year in Unit 1-2 this idea of going, all right, what is the relative molecular mass? and you went through, and if I go to this book here and I find my data booklet and I go to my, what is it called? My periodic table, you calculated these numbers. You did calculations last year. The relative atomic mass, you did this last year. You looked at isotopes, you looked at the percentage of isotopes and then found the ones that were relevant. That's really important. You did that last year. You understood isotopes. Isotopes are relevant still now. There are three main ones you need to know. The three main ones are carbon-12 and carbon-13. So these little tiny dots and spikes around them, because we put thousands and thousands of the sample through, you get lots of these little spikes that have got to do with the tiny little differences in carbons. Not super high yield and relevant to you, but it's good to know that's what's going on. These two are super relevant. So let's look at ethyl bromide first. So ethyl bromide, we understand there is a 1-to-1 ratio of 75 to 81. What's also really important about ethyl bromide, and something you need to know about bromine, is that there is a bromine 79 and a bromine 81. There is no bromine 80. But if you go to your data booklet and you find bromine, which will actually be over here somewhere, it says that the molar mass is about 80. So if you looked at that, you'd think, oh, there's definitely a bromine 80. There's actually not a bromine 80. There's only a bromine 81 and a bromine 79. There is bromine 80. It's very, 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 very rare. So given this 1-to-1 ratio, the average is in the middle. That's why bromine 80 looks like a thing, but it's actually not. And that's why you get this and this. And notice up here, both of these are technically your molar mass. Your molar mass, if you calculate it, will actually be this one here, because you will calculate your molar mass as your 80. You're not going to calculate it as 81 or 79. You're going to calculate it with the 80. So your molar mass, if you actually calculate it, will be in the middle here. So it's really important to remember that when you are looking at this and you're going, all right, my molar mass is one of these two, but the average between those is actually the number in the middle. So therefore, that's actually going to be the molar mass that I calculate if I were just calculating this based on the molecule. And then you have ethyl chloride. Again, these are both your parent molecular ion peak. They're both accepted. What's really important is that if you actually calculate it, you're actually going to get in here, because remember that the relative atomic mass is 35.5. So you're actually going to find that your sample or your answer should fall in between there, knowing that it's chloride. So it's really important you remember these isotopes and how they affect what you're doing. All right, let's move on to infrared spectroscopy. How are we doing? We've done about half an hour, which is good. So let's look at infrared spectroscopy. Now, I'm going to put sort of just a bit of a disclaimer. I found infrared spectroscopy really difficult in high school. I found it the most difficult. I think it's actually quite simple. And what you need to realize is the more you do exams, the more there's only really 4 or 5 different IR specs they're ever going to give you. There's not really a lot. So what's really important about IR spec? A couple of things. You need to know about 3 or 4 distinct waves. There are 3 or 4 distinct waves or peaks or troughs, whatever you want to call them, that are important. They are the 3 or 4 ones that are going to come up every single time, and we will go through them. Now, what else is really important? Everything below 1500, so 11, 12, 13, 14, 1500, everything below 1500, it's about there, is irrelevant. Why is it irrelevant? This is referred to as the fingerprint region. I hope you know this by now, but the fingerprint region is the region of which the fingerprint region is the region of which you can delineate very specific molecules. So let's say you had propanol versus propantuol. So the OH group or the hydroxyl group is on the final carbon or the first carbon versus the middle carbon. They're both going to show exactly the same at this part. Everything here is going to be the same. Everything here will be slightly different. Now, how is it slightly different? Beyond the scope of VCE. You don't actually need to know, and that's really, really important. That everything below this is completely irrelevant to you and you do not need to look at it. So please do not. Now, how does IR delineate itself from mass spec? Well, mass spec we bombarded with electrons. We actually didn't use EM, so we didn't use any electromagnetic sort of spectrum radiation and waves. We actually just used electrons, so technically it's not a spectroscopy. But IR spec does, it uses infrared. Now, infrared is a really weak energy. It's really weak. It doesn't have a lot of energy in it. So what you actually find from this is that when you are smashing this sample with IR spec, it's actually not a lot of power. You're not getting a lot of energy into it. So you really only change the way that the bonds are vibrating. So the bonds will vibrate differently according to how strong their bond is. Now, what's the most common strength feature to a bond? Well, I like to think about it like this. If I tied a rope, if I had a cliff, a really small cliff, and I had a meter between the two cliffs, and I put a car on each side of the cliff, and then I put a piece of rope in between it. Now, if I then hit that rope, how much is that rope going to actually sort of pull, and how much of it is it going to sort of coil and move around? Well, I've got two cars that are not going to move from just me hitting that rope. So it's not going to move very much. Now, what if I had two humans? You've got a car that weighs a couple of tons. You've got two humans that weigh, 60, 80 kilos, whatever they weigh. And those two humans have the same string between them. And I hit that string, it's going to move a heap more. It's just going to move way more. Why? Because the two humans weigh a lot less. So the amount of energy I'm putting into that string or the rope is the same amount, but it's moving it a lot more because the two things on either side are not as heavy, they're not as stable. So the one thing that's really important about IR spec is that what changes how these bonds vibrate is all got to do with the molecular mass and the strength of the bond. Now, obviously, there's other things that increase your strength of bond, but molecular mass is probably the most important one. So looking at this, just going back to the fingerprint region, so I think this is really high yield. You don't need to know what the fingerprint region is. So you see there, exactly, they look pretty much identical. You pull those away and you find that you actually had propan 1-ol versus propan 2-ol, the example I said before. So literally just the position of the OH has changed this, as you can see there. So let's go through the examples I want you to know. So there are distinctly 2 to 3 examples I want you to know. So the first example is the stiletto example. Now, the stiletto example is this here. You have this wider bond at around 3,300 to 3,600, somewhere around there. This is referring to your OH group. Now, how do I know that? Because my data booklet. So let's go to the data booklet. So I go to my data booklet and I scroll all the way down to here. And I find that between this bond here falls, or this peak falls at about 3,100, 200, 300, about 3,300 to 3,400. 3,300, 300, 400 is any of these ones here. Now, really importantly, I know from this shape that it is this. It is this. I know from the shape of this, IR spec, this is an alcohol, which has been confirmed by up here. This is most definitely an alcohol. This peak here refers to the alcohol, the OH. So it's this bond in here that is vibrating. This here at about 2,900, 3,000 is referring to each of the CH bonds. So it's referring to each of these. That's the vibration from each of those. So what's really important here is that this shape, this stiletto shape, this is what they refer to as a stiletto. This is the foot and this is the heel. This is the stiletto shape. This is always an alcohol. The likelihood of this coming up is huge. This always comes up for some reason. They just love bringing this one up. So it's really important that you know this. So really important, this is that stiletto shape. So understanding that, we then go, all right, what about everything else? Well, if I find 1,500, 1, 2, 3, 4, 5, if I find 1,500, literally everything else falls below 1,500. None of this is relevant. There's nothing else here. I'm happy this is an alcohol. Bang. Now, butanoic acid. So here I've got an oic acid. So what's really important with an oic acid is you've still got an OH bond and you've got this double bonded oxygen. So going back to my data booklet, I find that in this one, the OH acid it's a lot larger of a range. Now, this does not necessarily mean that it's going to fall at 2,500 or 3,500. There's just a bigger range. And because of that range, what we actually find is that 90 to 95% of the time, and in nearly every example VCAR has given us, oic acid engulfs the CH bonding. So this still has CHs, which should fall around 2,800 to 3,900. And what you find is this here is actually the CHs. If I drew it like this, and then drew it like this, I've pretty much got the same shape. This here is your OH from your acid, and this here is your CH from your CH bonds. But the thing is, this OH is actually bigger. It actually is somewhat like this. And because it's somewhat like that, it engulfs this CH bond, and it makes this really large bond. So if I then go and rub all this out and make it look a little bit nicer, what you find is that this one massive bond, I'm going to change colors, I'm green. This one massive bond engulfs both the OH and the CH. This does not happen in alcohols. Alcohols are distinctly different. They always have this doubling. Butanoic acid or oic acids in general, so carboxylic acids, will 90 to 95% of the time engulf and have this massive, massive peak. Now, there are times where it's different. When do those times happen? Completely random. But in this case here, you can see it. You can see in this case here where actually the OH bond has been very skinny and the CH bond is still present. This happens about 5% of the time. It's not very common. So thus, this is the one I want you to remember. If you've got a massive peak that centers around 3,000, 3,100, 2,900, you've got a massive peak in that area, it is going to be a carboxylic acid. Now, how do I confirm this is carboxylic acid? Let's find the fingerprint region. 1, 2, 3, 4, 5. Draw my line. Oh, there's another relevant peak. What is this? It's about 1,700. Well, let's move across and let's look at 1,700. COO, part of my acid, 1,700. This really strong skinny peak at around 1,650 to sometimes it gets up to like 1,850 is always a C double bonded to an O. So if you've got this massive peak here, which you know involves an OH and it involves a CH, and then you also have this peak here that involves a C double OH, do your maths, you put it all together and you do your investigation, put your detective hat on, the only option you've got is butanoic acid, or an oic acid technically, a carboxylic acid. So really important in this case here, you know you've got a carboxylic acid. So what about that COOH? Well, in this case here, I have, again, my fingerprint region, 1, 2, 3, 4, 5. Draw my line through there. I've got a little one here, but it's probably not super relevant. I've got a little one here. Again, this is probably just artifact. This is not relevant, so I wouldn't look at these. I wouldn't look at this. This I would. I would say this here is your CH bonds. It's at about 3,000. That makes sense. This here, again, another super skinny, strong peak here. Now, again, I know this is a C double bonded to an O. Now, you might then go, all right, well, what about a carboxylic acid? Well, I don't have that big peak here. This is nothing, and I've only got CH. So straight away, I'm ruling out my acid. I can't have an acid. So what have I got? Probably got a ketone or an aldehyde. And in this case here, I've actually got a ketone. So I've got acetone. This is a ketone. It's got the double bonded O in the middle of the molecule, and thus that is what you need to know. So what do I want you to take out of this? I want you to take out of it the 3 different examples I've shown you here. The alcohol example, the carboxylic example, and anything that's got this super strong skinny peak at around 1,700 approximately, can be down to 1,600 up to like 1,800, 1,900. This is a C double bonded to an O. This has to be one of your options that has it. So you got to think about your options. Aldehyde, ketone, ester, carboxylic acid. You've got all your options here, amides. All of your options that have that COO bond are here. Now, they all sort of overlap with each other, so it doesn't make it super easy. You've then just got to use that as sort of like your elimination method. I have all these things. What if I know already that my molecule doesn't have a nitrogen in it? Well, then I can rule out that it's going to be an amide. What if I know that my functional group is in the middle of my molecule? Well, then it rules out aldehydes and it rules out acids. I've really only got left ketones and esters. So knowing these pieces of information allows you to then add on and rule out things and rule in things from this. And that's how you want to use IR spec. So then let's talk about NMR, or nuclear magnetic resonance spectroscopy. Now let's be really blatantly obvious here. This is difficult. This stuff is hard. This is easily the most difficult of the 3 different types of spectroscopy. And again, today I'm not going to go through in detail how to do it and all the nitty gritty of it. That's not what I'm here to do. I'm here to just go through what is the most relevant pieces of information I want you to obtain for when you sit your exam, and thus makes you feel comfortable. So NMR spectroscopy, really important. You need to remember there are 2 types, and you need to be able to identify the 2, the carbon versus hydrogen. Carbon goes up to like 200, 180 usually, as you can see here. Hydrogen goes up to like maximum of 20, usually up to like 10 or 15, as you can see here. Really important. There are 3 environments in each of these, because this is not an environment. Please do not think it is an environment. Even if it is not labeled as TMS, if there is a peak at 0, it is not an environment. It is the standard. Super important. The other thing to help you identify, carbon does not split, hydrogen does split. So hydrogen splits, carbon does not. Really important. So I think actually being able to identify environments without looking at looking at the spectrogram is really important, because sometimes you do get asked to identify how many environments there are on something without actually looking at the spectrogram. And I think it's a skill that is at times forgotten. So let's go through some examples here. You are welcome to pause your screen right now and have a go at it. And I do really, really suggest that. So if you want to, and I promote it, pause right now and have a go at identifying how many hydrogen environments are in these 4 molecules. And then we're going to go through it. All right. So let's go through these. So let's look at our first one. First one, I'm just going to go through very quickly. We've got 3 groups of hydrogens. They're all in groups of 3. So again, that's a bit of a flag that maybe they're all the same. And it's what they're looking at. This is how I think about it. So this is one group. I kind of include the carbon in it. So looking down from there, what do I see? I see a carbon attached to a Cl, attached to a CH3, attached to a CH3. They're the 3 things that are attached to that carbon. Now, if I look at it from this angle, what do I see? I see a carbon attached to a Cl, attached to a CH3, and another CH3. So the 3 things I've got are the Cl and the CH3. It's exactly the same. If I look at it from this angle, it's the exact same thing. So again, it makes it very easy to identify there is one. Moving down here, this is where things start to get a bit different. Now, first of all, this is always in a separate environment. So that's 1. And then if I look from the angle of this CH3, I'm seeing CH2OH. There's no other CH3s. There's another one. So this is another environment here. These are the 2. Are they different or are they the same? Really important. This CH, if I look down here, what am I seeing? I'm seeing a CH2CH3. Now this CH, if I look down here, I'm seeing a CH3. But if I look this way, I'm seeing a CH2OH. And if I look this way, I'm only seeing an OH. They are looking at different things. They've got different perspectives. Given they've got different perspectives, this is 1 and this is 1. I have 4 hydrogen groups. I don't know why I went the other one, but nonetheless, I have 4 hydrogen groups. It's the same thing on here. I'm not seeing another CH3. I'm seeing a CHCl. This one I'm seeing a CH3 and not another CHCl. Thus, there has to be 2. And in this last one, this hydrogen is definitely going to be in its own environment. There's nothing else with one hydrogen. But are these 2 the same? I would say yes. They're both looking at a CHCl and then a CH3. And then this one is also looking at a CHCl and then a CH3. So I would say these 2 are definitely in the same environment. They are. You've got 2. So now let's look at carbon environments, cleaning that up. So carbon environments, really importantly, they don't always match your hydrogen environments. And I think that's another thing that's super duper important. I find at times there's a lot of students that I sort of teach and tutor that come in and say, oh, the hydrogen and carbon environments over the years have said to me that the carbon and hydrogen environments, like I found the hydrogen environments, thus the carbon environments are the same. That's not how that works. They are different. Sometimes they will be the same. That's just a coincidence. It's really important to understand that things are not always going to be the same. So in this case here, what you can see is that once again, this, and this were the hydrogen environments. I actually think all these carbons are the same as well. These carbons have 3 hydrogens coming off them and they see the exact same thing. So I'm comfortable with them being the same. But you've got an extra carbon in here. This carbon is distinctly different. It's got nothing to do with the others. You've got 2. Coming over here, same process. This carbon has distinctly different things coming off it than this carbon, so they're going to be different. Again, here, you've got a carbon that's got a CHOH, you've got a carbon with a CH2, and you've got a carbon with a CH3. It's going to be different. And then lastly, this one actually matches very well, but this one has the same thing coming off it as this, and they both see the exact same thing. So it's what they see, they're seeing the exact same thing, so you've got 2. So remember, our hydrogen environments were 1, 2, that looks like a Z, but that'll do as a 2, 4, and 2. I don't know why that looks terribly like a Z, that'll do. So these 2 matched, just a coincidence, but these 2 didn't. These 2 did not match, and it's really important to understand that with these 2 not matching, none of them technically could ever match. So it's really important to understand that you cannot just say, oh, I know the hydrogen environments, thus I know the carbon environments. It's not how it works. All right, continuing to move on. Let's quickly talk about TMS because you do need to know a little bit about TMS. What do I need to know about TMS? You need to know how to draw it, first of all. So it looks like that. So you've got your SI in the middle. I think it's like silicosis or something. I never really know exactly what it is, but you don't really need to. But you've got your SI in the middle, and then you've got your CH3s around it. This makes this molecule very protected. This molecule is extremely protected. It's got lots and lots of shielding, and thus it results in it being really, really upfield, and being really, really upfield makes it it essentially makes it stronger than any of the other ones. So thus it's always going to be at 0. So you're always going to find TMS at 0. Now, really important, most to nearly all VCAR exams will have a TMS peak. A lot of them will label it, some of them won't, but they will always have a TMS peak. A lot of ones that you find online and a lot of exams online and so forth, they don't actually use the TMS peak anymore. They just assume that you know that 0 is that, and they just don't put it there. But it's just really important to understand that if there is a peak at 0, it is TMS. It's the reference compound. It stands for tetramethylsilane, so it's silane. You do need to know it. You need to know how to draw it. You need to know the structure of it and the importance of it. There are 3 things you need to know, and you do need to know them. You cannot get away with not knowing that, unfortunately. So you do need to know that. And then quickly just splitting in hydrogens. I think hydrogen NMR, people forget about splitting a lot. So a couple of really key rules. If you've got an OH, which commonly comes up in these, it's always never going to split. So as you can see, that's always going to be that one there. If we look at the others here, we've got a splitting into 3, a splitting into 3, a splitting into 5, and a splitting into 1, 2, 3, 4, 5, 6. So we've got a splitting into a 6, and we've got a splitting into a 5, and a splitting into a 3 and a 3. So what are we actually going to have? So I can tell you now, this one will split into 3. So each of these are in different hydrogen environments, by the way, because there's no symmetry. So this will split into 3, this will split into 5, this will split into 6, and this will split into 3. I can tell you that now because of the neighboring. So if you look at that, you have that splitting into 3, you have that splitting into 5, that splitting into 6, and that splitting into 3. So really important, you can identify what your environments are from your spectrogram if you just know the splitting. I don't even need to go to my data booklet and go, hey, where is all my NMR? So as you can see, here's my carbon NMR, here's my hydrogen NMR. I don't need to go here and look at this. I don't need to look at my chemical shift. So it goes up to about 13, so it goes up to about 200. I don't need to go and look at that. There's no need to do that because I can just literally look at the splitting and use my N+1 rule. So using your N+1 rule is a super high yield skill to do. So please do it when you have the opportunity to do it. And that is NMR. So let's quickly go through a practice question. I have literally discussed the answer to this. So which of the following is the has the greatest impact on the peaks shown in the IR spectroscopy. So I want you to have a go at this. Take your time, give you an opportunity to pause, 3, 2, 1, pause. And hopefully that was enough time to have a go. So in this case here, we talked about the whole idea of that rope in between two objects, and we talked about that ability for those objects to be stable was based on their weight. In this case, when we talk about weight and we talk about our molecules, we talk about molar mass. As such, heavier bonds, harder to vibrate. As you can see here, there's some other things here that are really important. Electronegativity does not affect bond vibration. The charge is all about mass spec, really important, and the magnetic spin is NMR. So your answer here is C, that your molar mass is the most important thing. Now, lastly, I'm not going to go through this, and you're welcome to go through it yourself. You can find the exam, you find the examiner's report. But I just wanted to show you that this is what VCAR gives you. They give you each of them. So in this one, they actually didn't give you any mass spec, but they give you each of them, and then they talk you through them. They talk through this, and they talk through this, and they talk through this, and they eventually end up with you getting your answer. And it says, consistent with all the evidence provided. And they essentially giving all of this to you as evidence. So if you looked at this here, I can tell you right now that you have a COO and you've got a CH. So you've got some sort of ketone or aldehyde in this case here. And then from there, you can start to determine, all right, what else is going on here? Well, I have 3 carbon environments and I have 3 hydrogen environments. So how do they work? And as you can see here, that's literally a question. They're giving you all of this information. They've even given you a table here. This table tells you how many hydrogen environments there are. There's 3 rows, so there's 3 hydrogen environments. That's a free mark. So you would go through and say there's 3, using the IR on page 7. This is an old exam, so it's no longer on page 7. Identify the atoms and bonds between associated with the labeled A. So you'd write C double bond O. It's literally what you would write here. You'd write C double bond O. I know that's terrible writing. You'd put 3. I've literally gone through this in about 15 seconds and I've got 3 marks. That's how quickly and easily these marks here. Then it says the signal at 1.3, what is the number of equivalent protons bonded to the adjacent carbon? Well, 1.3 is just split into 3. So I can tell you there's 2. I've got 4 marks straight away. These are 4 extremely straightforward marks that you should not be missing. This is where things start to get a little bit harder. It says draw the group of atoms that are giving rise to the triplet and quartet splitting patterns. So you need to start to think about, all right, what's going on with this triplet and this quartet? What am I actually getting out of it? And then from there, you can also go on and do, all right, propose the structure of compound X, and you can do it from there. But nonetheless, you've been given so much information here, you've just got to go through and pick it apart and figure out what is going on. They've even said that the molecular formula is this. They've even given you the molecular formula. So they're making it very, very straightforward for you. In this case here, you actually end up with an ester. That's what's going on in this molecule. So it is an IL-08. And you can go through and figure that out for yourself by looking at all of this information here and going, all right, what's at 160? What's at 9? You go to here, somewhere around 9. I've got this idea here of a, where it is again, here. Well, actually it's not, but you're talking about some slightly different stuff here. But what you find is that this is an ester. There's probably slightly different data booklet, and it's why that doesn't match perfectly, but in the end, you're still going to be able to figure that out. So let's continue on to volumetric analysis. This is your last step. So volumetric analysis. So we talked about identification. We've talked about separation. This is quantification or quantifying. So we're figuring out concentrations and amounts. Yes, we can do a little bit with chromatography, but this is much better. So volumetric analysis, I hope you went through it last year. I hope you've gone through it in super detail. This is super duper high yield. They just love these questions. Why? Because the maths is easy, straightforward. If I told you what to put in your calculator, you'd be able to do it. It's like multiply 0.5 by 15. You could do it. It's figuring out what numbers to put in that is really, really difficult. The maths itself is very straightforward. It's the figuring out what I need to put in the calculator, what I actually need to do. And I'll give you a couple of hints on what to do. But before that, let's just talk about some key things you do need to remember from last year. So you do need to remember your acid base. You do need to remember your pH sensitive indicators. These are in your data booklet. I know this data booklet came out very late in the year, so some of you may have not have looked at it in super detail, but you will find the acid base indicators have barely changed. I think they removed one, so really not a big deal. You'll find them all here, page 5. They have each of the indicators and the pH range which they change. So really important, you do need to always go back to that and find that there. So volumetric analysis is relevant for your pH indicators, but it's also relevant for a standard solution. So you do need to remember your standard solutions from last year. Remember that your standard solutions come from a primary standard. So you need to dissolve a known amount of primary standard and a known amount of water, but it really needs to be that sort of sterile, perfect water without anything in it. By performing a titration against another standard solution in order to determine the exact concentration. Cool, comfortable with all that. Awesome. There's also some terminology you need to remember from last year. I'm going to put these up on the screen. I'm not going to go through each of these. I don't need to, but you do need to know them. So if it's something you don't know, take a screenshot or make sure you have them on flashcards or something so you can go through and remember them. You do need to know each of these words. They do come up and they are important to use correctly. If you don't use them correctly and you use the wrong word or the wrong terminology, you will lose marks. Now, as we talked about, you need an appropriate pH sensitive indicator. Most indicators themselves are weak acids or bases and their conjugate forms have different colors. Again, I don't need to go through this in super detail. You get that change in color as you get to that range. You need to know your difference between your equivalence points. So remembering back here, your equivalence point is where the reaction is exactly a stoichiometric ratio. Your end point is where the change in color. These are not going to be exactly the same, but they're going to be pretty close. So when you actually do a titration, this is what you calculate. This is what you find. This is if you were doing a perfect calculation, you would find this as your equivalence point. And that's why there's differences between the two. Now, you do need to remember these little diagrams from last year. Which one of these is useless? It is this one here. A weak acid and a weak base means nothing. A strong acid and a strong base is easily your best titration. This is the best titration by far. You get this straight line and we love it. A strong acid and a weak base and a weak acid and a strong base, they're all a little bit, they're not as good, but they do work out. Now, what's really important is these lines don't always go up. Sometimes they go down. Why do they go down? Because sometimes they'll start with the base. Sometimes the base will be what is in your conical flask, the one that you're actually mixing in. So really important, this is the pH that's in your conical flask down at the bottom. I believe it's a conical flask. It's this one down here. Yes, this is your conical flask. So that's where the pH is coming from. Really important. It's not coming from what's in your burette. This is coming from what's in your conical flask. So whatever's in your conical flask will be what your pH starts at. So in each of these ones, the acid is what is in your conical flask, and you've got your base in your burette. Now, you do need to do some memorization here. You do need to know an example for each. So you need to know 4 examples. Now, hopefully you remember them from last year. If you don't, I want you to pause right now and have a quick think. What are my 4 examples? You may not know a weak acid and a weak base, and that is okay if you don't know a weak acid and a weak base, because generally, I remember when I went through Unit 1, 2, I was only really taught the strong acid and strong base, and then I only learnt the weak acid and weak base when I came to 3, 4. If you don't, that's okay, but you should know an example for each. We will go through each of them. So as you can see here in this question, you've got a diagram below that represents a titration curve. We've started at a base here, and then we've got to a really strong acidic point. So in this case here, I would say we've started with a weak base and we've got a strong acid because we've ended really strong and we don't have a really nice curve. So therefore, we definitely got a strong acid. The strong acids here are the HCl's. I hope you remember that from last year. HCl is always your strong acid. We're not looking at ethanoic acid as our strong acid. That is our weak acid. So that gives you your answer for your weak acid there. Then we need to look at which is your strong base and which is your weak base. I hope you remember your strong base from last year was NaOH, sodium hydroxide. That is your strong base. Thus, process of elimination, your ammonia is your weak base. Your answer here is A. There's your little hint. This is what you need to remember for this year. HCl, strong acid. ethanoic acid, weak acid, sodium hydroxide, strong base, ammonia, weak base. So you do need to know these four. It helps you answer questions. This is a VCAR question. I should have wrote that up here. I do apologize. This is a VCAR question from a couple of years back, and you do need to remember each of these. This was the expectation in this question, was that you remembered this. All right, from here, really important, you got your sample. You need to, from here, sorry, it's really important, you need to remember how to go through a titration. Now, this might seem silly, and you might look at me and be like, why are you teaching me how to go through a titration? Why am I teaching you to go through a titration? Because as I said before, it's super high yield, and the maths itself isn't necessarily difficult. I don't think the maths is the actual calculations you're doing are not hard. It's understanding what calculations you're doing. And I find the easiest way to remember it, and the method that I found has worked best for students, is doing a diagram. And if you put a diagram on a page showing step by step what you need, what has been done, you can then follow that diagram backwards or forwards accordingly and do your calculations. So I always have a little diagram. I always draw one when I have a titration question, even if it's just purely maths that I'm doing. And so as you can see here, your diagram should always start with a sample placed in a beaker. And then sometimes they will then take a pipette of that sample. Sometimes they'll just place the whole sample in your volumetric flask. It's just dependent on the scenario. Sometimes this second step is skipped. So this is sort of like the optional step. In the volumetric flask, they will always fill up the volumetric flask. It doesn't matter what they fill it up to. They will always fill it up to a number. So it'll be 250, 100, 1000, whatever it is. And they're essentially diluting your sample. They will then always take a pipette of the diluted sample. This step nearly always happens. I never put the pure sample in the conical flask. But as you can see here, I've got it diluted. It's no longer that dark green. It's a little bit lighter. I've put that pipette into my conical flask. And then from there, the titration occurs and you get your titration. Now, it's really important to remember when you have a titration, and let's say this is at 20 and then this is at 19. If my burette looks like this, it's not perfect, but I would say this is around 19. Now, if you had little dots, you could say that's 19.1. It's where this is at its lowest. You don't look at these bits up the side. It's not that there. You always say where this convexing is at its lowest, or concaving actually. It's concaving, not convexing, isn't it? Whichever one it is. You're always going to treat it where it's at its lowest, and that is the number you're going to use, and it's really important that that's what you do. And that there's your resolution, remember, because if I have no dots in between this, my resolution of my burette is 1 mil, because I can't actually accurately say what is in between 20 and 19. Now, if this burette had points, which most of them do, at 19.1, 19.2, 19.3, my resolution is 0.1. So in this case, I'd be pretty accurate in saying this is 19.1. So that's your resolution. That's another word you need to know. It's part of experimental design. It does come up. So you do need to know what the resolution is. Now, that is everything to do with your analytical chem in terms of your identify, your separate, identify, and quantify. There's also a bit of redox, but we're not going to go through it. There's a couple other points I want to go through. Now, there is medicinal chem at the end of this, and there is a little bit of other ways of doing, other ways of essentially identifying molecules, and I am just going to quickly talk through some of them. So I am going to talk about very quickly the iodine number, because it's brand new in this study design. I'm going to talk about stereoisomers, because we talked about isomers in the last lecture, the one that was in June, July. But this lecture, I want to talk about the next step, which is stereoisomers, because they've been split up. And then just very quickly, we'll talk about how that affects medicinal chem, but we're not going to go into super detail. So this is brand new, iodine numbers. So what's really important is that when you contain COO bonds, you're not saturated. We know that. We know we're not saturated. And unsaturated means there has to be one or more of these bonds. So using a similar logic, the degree of saturation is just measured by the number of double bonds plus the number of rings in a molecule. So if you've got rings, it obviously changes things up. So propene has the degree of saturation that has one double bond. Chlorohexane also has a degree of unsaturation of 1 since it contains one ring, although no C-double-O bonds. And then benzene has a degree of unsaturation of 4 because it's got 3 double bonds plus one ring. Really important. So the iodine number, that's not the iodine number, that's just the degree of unsaturation. So the best way that we can then visualize this is that sometimes we have compounds that we don't actually know how many double bonds, how unsaturated they are. So the best way to find the degree of unsaturation is to react the compound with iodine, because we know iodine will fill those double bonds and make them single bonds. So using this, we can calculate something called the iodine number, which refers to the mass of iodine in grams that reacts with 100 grams of the unknown compound. So if we've got 100 grams of an unknown compound or 100 grams of unknown saturation compound, and we react it with a massive iodine, it's essentially how much iodine gets used up. So for example, if we had 10 grams of oil reacting with 0.039 moles of iodine, then for 100 grams of oil, there would be 0.39 mole of iodine reacting. We're comfortable with that because we just multiply by 10. Since iodine number requires 100 grams of the unknown compound. Therefore, the mass of iodine is 126.9 times 2, because that's your molar mass, times by your 0.39. It's 98.9. So the iodine number of this oil, no matter how much, we're talking about 100 grams, but the iodine number of this oil is 98.9. That's just what it is. There's no units, just 98.9. The iodine number is 98.9. That is something you do need to know. It does come up. It's a bit of a weird concept, but it has come up. It's in the sample exam. So you do need to understand how to operate your iodine numbers. All right, isomers as well. We talked about isomers last time, which are the chemicals with the same molecular formula. We remember that isomers can be structural or stereo, and we talked about structural last time. So we talked about chain and we talked about positional and all that sort of stuff. Now we're going to talk about stereoisomers very quickly. Now, stereoisomers have been cut down to optical in this study design. That's all you need to know. Now, an optical isomer, now these are structural isomers, is very weird. So an optical isomer is essentially atoms that have the same things, the same molecular and semi-structural formula. They look identical, but they're different. And the best example I can give is my hands. Look at my right hand. What has it got? It's got a thumb, it's got a pointer finger, a root finger, a ring finger, and a pinky. That's my right hand. Now, what about my left hand? If I look at my left hand, it's also got a thumb, it's got a pointer, it's got a root finger, a ring finger, and a pinky. And they're all connected the same way. The pinky is next to the ring, which is next to the root, which is next to the pointer. Same thing, pinky next to the ring, next to the root, next to the pointer. They're all in the same way, but they're different. They're mirror images of each other, because if I go like that and I put my hands on top of each other, I cannot get my thumbs on top of each other unless I flip them around. Now we're not the same. So this is the idea that I've got the exact same semi-structural formula, but I've got a distinct little difference here. So notice how I've gone and I've changed the way these are connected. Now, if I try to put these on top of each other, they're not going to be the same. And this can only happen when a carbon has 4 different groups. So if I had a carbon that was a CH4, it's got 4 hydrogens, I cannot do this. If I have a carbon that is got an OH group, and then it's got a double bonded to an oxygen, and then it's got a hydrogen, it's got 3 different groups. That O, that double bonded oxygen, counts as 2 groups, thus it's the same, and thus it does not work. If I have a carbon that's got 2 hydrogens, and then an OH, and then a chlorine, again, doesn't work. I've got 2 hydrogens. I need 4 distinct different groups. In this here, I've got 4 distinct different groups. I've got a C double bonded OH, I've got a hydrogen, I've got an OH, and I've got a CH3. I've got 4 distinct different groups. So given I've got 4 distinct different groups, I can therefore work through this appropriately. So really important, optical isomerization, that is how that works there. So I've got all of this information, as you can see. The really important thing about optical isomers is they cannot rotate or twist. And what's also important is optical isomers, it's how do we identify them? It's a bit of a weird idea, but it's how they sort of, it's how they work with light and how they reflect light. It's a bit of a weird concept, but you don't really need to know that in super detail. Why is this relevant? It's relevant because in medicinal chemistry, when we have two different enantiomers, so enantiomers are two different stereoisomers. I should also say this is referred to as a chiral carbon. I hope you know this by now, but this is a chiral carbon. Why? Because it's got 4 different things and it can be an optical isomer. So if you've got optical isomers of a medicine, now 2 different optical isomers are referred to as enantiomers. In medicine, you'll sometimes hear them referred to as a left isomer and a right isomer, a positive isomer and a negative isomer, sometimes an S and an R. Medicine most commonly uses S and R. But notice how these are both ibuprofen. Now, if you know what ibuprofen is, if you don't know what ibuprofen is, it's Nurofen. Ibuprofen's actually the name of it. Nurofen's the brand. So ibuprofen here has 2 distinct different versions. So the difference is that this is very weird, but a thick line means coming towards you and a dotted line means going away. So what's actually happening here is these have just been put slightly differently. That's the only difference here. These are just going in slightly different directions. Because they go in slightly different directions, you actually have 2 different enantiomers. Now with ibuprofen, 2 of them are safe. One of them works more effectively, but they're both safe. Sometimes with medicines, one enantiomer is actually not safe and the other enantiomer is. So it's really important in medicine that you can identify which ones are going to work and which ones are not, and then safely use the one that is relevant. It's also relevant because enzymes break up medicines and medicines block enzymes, and sometimes enzymes can only attach to one enantiomer. So really important to understand that enantiomers and optical isomerization is really important when it comes to medicinal chemistry. Not going to go into any more detail with that. We're not going to talk about medicinal chemistry today just because of time restraints, but that is the relevance of it when it comes to medicinal chemistry. So we've now been talking for about nearly 80 minutes, so nearly an hour and 20. Got about 40 minutes left. If you need a break, I highly suggest it. Pause now, go and take a little sip, go get a coffee, whatever you need to do, and then you can come back. We're going to go through exam approach. So when I talk about exam approach, I briefly discussed it in the last set of slides, but I'm actually going to go through in more detail what I want you to do in terms of managing time, reading time, processing, and so forth. And then we're going to talk about some tough exam questions. We're not going to get through all of the tough exam questions that are on the slides. I put more than what I'd get through on purpose because I was like, well, if I'm a little bit short on time, I can push through it. But I also identified that if they're there on the slides are available. You're welcome to have a go at them. I've labeled the VCAR year they're from, so you can always go and look at the answers, but I've also put the answers on the slides, so you're welcome to come back to them. So let's push on. So exam approach, exam strategy, and understanding. I think what's really important is that at this point in time, I'm hoping you've punched through some practice exams and you know what you're sort of doing. Managing time is really important. I think it's very individual how you manage time. And there are points here where I say, I'm going to talk about some points later on where I talk about managing time in terms of where you get your marks and not. But I think what's really important is that you need to make up a mind on if you do them in order, if you jump around, whatever you do. But I think what you need to do is have some time points. And I think this is really important. Jot down a few milestones while you're in the exam. So when you start writing time, jot down, I want to be done with multiple choice at 9:45. I think the exam starts at 9. I want to be halfway through at 10:45, whatever it is. I want you to have some time points that you can be like, all right, I'm on track. I'm going well. Please do not just forget about the clock. Please do check the clock semi-regularly. Maybe once every 10 minutes, just make sure you're on track of where you are. I think this is sometimes forgotten, and I think sometimes people don't put enough emphasis into managing time in an exam, and they just say, oh, I'm just going to get as much of it as I can. If you've done enough practice exams, that shouldn't be an issue. You should be able to get through your exam pretty much perfectly, or a little bit early, or you might find you're a little bit short, but it's pretty good. But you need to have that time strategy down packed. So then when you get to the exam, you follow that same process and you're not changing things up. When I talk about that in this slide, have a process and stick to it. I think this really just means not to panic. So once you panic in an exam, it spirals very quick. I can speak from experience to say when you panic in an exam, you spiral very quickly. I did maths methods in year 11. And I got a relatively good mark, and I tutored it way back when. I couldn't talk about any math methods anymore because I've completely forgotten them. But my story from this is that being my first set of exams, I'd actually done the general exams before, but the general exams are very different. The time restraints are not there. But I remember I walked in and the first exam is an hour and it's no calculator. And I got through the first half of the exam great and I was feeling great. And then I got to the second last question or the last question, and it was a really difficult trig question. And I made an error really early on in this 4 or 5 mark question, and it absolutely butchered the maths from then on. And it became really difficult. I couldn't actually do any of the maths. It was so hard. And I panicked because I was like, what am I doing wrong? This shouldn't be this hard. I've never done a question this hard with the maths without a calculator. What is going on? And I panicked, and I panicked for probably about 5 minutes where I did nothing. And it took me 5 minutes to go, I need to stop. And I stopped for a minute and I just went, cool, let's just stop. Let's just move on. And I moved on to the next question. But by then, and I know this is 6 minutes, and you might say, 6 minutes is not a lot. This exam goes for an hour. Yes, you have 15 minutes reading, but this exam goes for an hour. I have now wasted 6 minutes. That's 10% of my exam. And that's really important because I understand from tutoring students in the past, I've had students who've come to me and said, I just did my English exam and I got a really bad article and I just panicked and I spent 15 minutes doing nothing because I couldn't figure out what to go with it. And I think it's really important you have strategies for that, because as much as mine was only 6 minutes, it's 10% of the exam. 15 minutes for you is, I'm trying to do my maths here, but it's also 15 minutes is 10%. So if you panic for 15 minutes, you've lost your 10% of your exam. You panic for 7 minutes, you've lost 5% of your exam. It's really important you don't do that. So if you do come across things that make you panic or things that really stress you out, you just need to have a strategy, whether that's literally when you identify you're panicking, identify it straight away, put your pen down, sit there for 30 seconds. I'd rather you lose 30 seconds than lose 6-7 minutes. 30 seconds is very minimal in the context of things. 7 minutes is not. So really important that you sort of identify it early, take that deep breath and go, all right, I'm going to skip this question. I will come back to it. I will come back to it in the last 10 minutes. If I panic in the last 10 minutes and I've done the rest of the exam, that's less detrimental because it's just this one question, which I was struggling with anyway. But if I panic now, I'm going to struggle a lot more. So identifying those things is really important. And when you stick to a process, you can generally finish the exam in a good time, which means you can sometimes have time to proofread. And I think that's a really important thing. Particularly those of you who are really strong and can finish the exam quite quickly, you can really attempt multiple choice questions more than once and make sure your answers are correct. Also, really important, checking that, because the multiple choice is answered on a little sheet where you fill in a bubble like NAPLAN. Really important that you check that you've filled in the right bubbles, because sometimes you will not fill in the right bubbles. And if you don't fill in the right bubbles, it can end your world very quickly. So really important. Please use reading time. I don't know how many more times I need to say this. I've been tutoring for 6 years and I still say this now. Please, please, please use reading time. Do not waste your reading time. Reading time is an extra 15 minutes. It's a bonus 15 minutes. It's how I treat it. I think you get a bonus 15 minutes in your exam. Use it. So reading time is essentially just this extra time to start doing questions. This is how I did my reading time. I was a little bit OCD, so I check I have all the pages in the question book. It's a bit of a weird thing. That's just what I did. And then I would generally go and read my redox question. Why I struggled with redox. Going through redox was clearly my worst topic. And so therefore I went to the redox question first. I was like, I struggle with this the most. So if I'm struggling with redox the most, I need to go and spend time on redox. So going and spending time on redox allowed me to essentially do the best I could. So once I went through and I did my redox, I would then read any of the really big questions. So if there's a 5 or 6 mark question, I would go through and I'd spend my time on it. And I go, all right, I need to spend time on this. I'm going to read it. And thus I have an idea of what it is. So then when I get to it next time, I can actually just read it again and I will pick up things I didn't in my first read. So that's my second thing. And then my third thing, or my fourth thing really, was I just begun multiple choice. You don't have your calculator. Really important. You do not have access to your calculator and you cannot write anything down. So if the multiple choice was maths-based, I wouldn't do it. Maths-based multiple choices, don't do it. But if I had if there were questions that were just, true or false questions, or questions where they were just elimination questions, I'd literally just go through the exam and I'd go, all right, question 1, I can do that one without using a calculator. And I'd actually do it. And I go, all right, I remember question 1 is B, question 2, C, question 3, oh, it's maths, skip it. Question 4, D. Then when the exam starts, I can quickly, when the reading time starts, I can quickly go to my book and go, all right, B, C, D, done. I've already done 3 questions. You can usually get through 4 to 6 questions, I'd say. If you spend a good 10 minutes, you can get through 4 to 6 questions. You get through 4 to 6 questions, you've got, let's say you get through 5 questions, you've got 25 multiple choice questions left to do. And if you've allocated 45 minutes, you can definitely punch those out quicker than that, and you're ahead of your time frame. So please use your reading time. Please practice using your reading time. Please do not go into the exam never having practiced reading time. It's a terrible way to go about it. And then this is a question that always comes up. Do I do the exam forwards or do I do the exam backwards? And I think sometimes I probably get a little bit frustrated by people always asking me it, funny enough, but I actually think it's a very, it's a valid question. And I think what's really important is that for all of you, you just need to pick what works for you. What works? Do I much rather this exam forwards or do I rather the exam backwards? And when I say backwards, do I rather doing the writing time first, the short answer first, or do I much rather doing the multiple choice first? It's totally up to you. My big thing is that with the multiple choice, you need to have a time frame and say stop, because you would rather leave multiple choice questions blank, so then at the end you can quickly guesstimate. In a sense, you can sort of like read through the question very quickly and go, all right, I think it's B or C. I can't do that off the top of my head very quickly. I'm just going to go B or C. That's if you're really struggling for time at the end. You can get marks. You can't just do that with a short answer. You can't go, all right, I've got no, I need to think about this. I'm just going to write down something. It's probably not going to get you marks. So really important. I think the most important thing here is you need to pick one and stick with it. It's individual. I went forward to back, but a lot of people I know did short answer, then multiple choice. It's totally up to you. And then you'll also ask me, what was that exam? This is the VCEE 2024 sample exam. They did release a sample exam in 2024. So it's really important that you have a look at it. There are no answers to it. You can always ask your teacher to go through and potentially make you some answers or so forth. Or if you've got a tutor or whatever, you can also ask them. But you can find that the 2024 chemistry exam, being the first year of the study design, there is a sample exam. And then exam practice, please make sure you make it count. I've already just briefly discussed it, but using reading time, please use reading time. I don't know how many more times I need to ask this. Just please use reading time. It's like the most important thing I can tell you. Reenact exam conditions. Please do not have your phone there and then suddenly start scrolling through TikTok halfway through it. Please don't. You need to sit through an exam for 2.5 hours. You need to know how to sit through an exam for 2.5 hours. If your first exam you're sitting through for 2.5 hours, or 2 hours and 45 technically, is the actual exam, you're doing something wrong. Please, please, please reenact exam conditions, especially now. I think the first couple of exams you did, totally fine. Do them open book, spend a bit of time, take some breaks. That's okay. You have now reached this point where your exam is in, 5 weeks, 6 weeks. You should be doing exams under exam conditions. Your English exam is in 3 to 4 weeks. If you're doing English, Englang, and Lit, I think are all at the same time. Your first exam is probably in like 3-4 weeks. You need to be doing exams under exam conditions, especially for those bigger exams. Like English in that, you need to be practicing sitting an exam for 3 hours. That's the reality. So please be used to doing that. You need to practice sitting exams under exam conditions and doing the full time frame. I especially think once school ends, because there will be a point, you probably have 2 or 3 weeks and you have a week or 2 weeks off before. Please practice at the time the exam is. Wake up in the morning like you're going to sit the exam. If the exam is at 9 in the morning, wake up to do the exam at 9 in the morning. I think that really helps. Correct the exam yourself. I understand subjects like English and psychology and some of those like humanities, geography ones where there's like essays. That's a bit different. And I understand that because to those exams, it's difficult. You kind of can't really judge how you're going. Chemistry, there is a right and a wrong answer. Yes, some of the paragraph ones are a little bit more wishy-washy, but 99% of the marks are right or wrong. You talked about this, you didn't talk about this, etc. You can answer your own exams. The exam answers are there. Please, please, please mark your own exams. That is how you will learn. If you do not mark your own exams, you will not learn. And I think that's a really important point. I think there's a lot of students out there who think, oh, I'll just get my teacher to mark it and then I'll just look through my mistakes. No, you want to keep bettering yourself. So I want you to be harsh, but not too harsh. Obviously, I don't want you to be like ripping yourself marks, but you should have been giving yourself marks. But you need to be realistic that I need to work hard. And that's the only way I can work hard is if I actually go, all right, let's have a look at why I went wrong. Let's have a look at marking this and going, where are my errors? Where did I actually think I did well? And you can also go like, I spent heaps of time on this question, but I didn't do very well. Whereas I didn't spend a lot of time on this question, I did well. You can start to identify areas where you actually need to sort of spend a little bit more time, spend a little bit less time, etc. So it's really important you answer your own exams, mark them yourselves. Really, really, really important. And then reflect on your mistakes. Please review. There is no point doing an exam if you're not going to review your mistakes, period. If you don't review your mistakes, what was the point in doing that exam? So please review all mistakes that you make. You're going to learn heaps from it. And then this is a very contradictory point. I've always said that I think when you are doing an exam, if there's areas of concern, you can spend a little bit more time on them because you'll make up time in other places. But if you're a bit tight on time, you're someone who finishes, sometimes 5 minutes early, sometimes 5 minutes after. So you push your exam limits. Please, if you're getting tight in the end, go to the questions where you get marks. Go to the topics. Don't go and waste time on the topic that you struggle with the most. If the topic you struggle with most is redox and you've got a redox question and you've got an equilibrium question left at the end and you've got 10 minutes, do the equilibrium question first. That is going to get you marks. That's where your marks are. That's your area of strength. You always get full marks on those questions in your practice exams. So go and spend your time getting your marks there, and then whatever time you got left, do your redox question. If you miss out on a few redox marks that you might have got, that's okay. So be it. There's probably a couple of questions there you didn't do, which you wouldn't have got marks from because it's a tougher topic. That's okay. That happens. But if you spend your time on the questions that you're going to get marks on at the end, do it, because I want you to get the marks, the fullest potential of marks you can. So if you're running out of time, go to the questions you will get marks from. And if that's a couple of multiple choice questions, you got 10 minutes left and you got a redox short answer, which you know you're going to struggle with, and you read the first part of it and you go, I'm really struggling, versus you got 5 multiple choice questions that none of them are redox, they're all, different topics. There is actually worth in going back and saying, I'm just going to do this multiple choice. There's 5 marks there, there's 8 marks here. I'm probably not even going to get 4 of those 8. I'm struggling with that question, whereas I can get 5 out of 5 there. So quickly go and do those 5. And then if you've got 3 or 4 minutes left, you might get 1 or 2 of those redox questions. So really important, go back if you have to and get the marks that are there that you will guarantee getting. So really important. Sometimes you do need to focus on the easy marks when cut comes to chase. Please make sure you do it because they're marks you can get. All right, now in the last, how long have we got? Last 20 minutes. We've got about 25 minutes. Let's go through some tough VCAR questions. So what I'm going to do with these is I'm going to put this question up on the screen. I'm going to read it and I'm going to say, all right, pause now and have a go. And I'd really like you to pause and really like you to have a go. I think that's the best way you're going to learn. So please, please, please do pause. Please do have a go. And then we will go through each of these questions. So our first one here is a 2021 Northern Hemisphere exam. So Northern Hemisphere exams are the exact same. They're run in the middle of the year there's a couple of schools in the Northern Hemisphere that do VCE. So their exams are a different time, all on the same curriculum. So it says here, high-powered liquid chromatography, HPLC, has a non-polar stationary phase and a polar solvent in the mobile phase. Which of the following substances would have the lowest retention time? Now, for context, 16% of people got this correct. 16%, it's extremely low. So when you have a go, you've got a polar solvent phase, which would have the lowest retention time. Lowest. All right, 3, 2, 1, pause. And hopefully you are back. So we have a polar solvent mobile phase and we want a low retention time. That means we need something that is polar. We don't want non-polar things. We want polar things. So let's look at what we've got. Hexane, non-polar. Tetrachloromethane, that's 4 chlorines around a methane. That makes it non-polar because they've all got the same. So non-polar. So we've got these two. We've got chloromethane and bromomethane. This is a tough question. And I think I need to go to my electrochemical table. Now, what do we know about electrochemical table? We know that this is the most electronegative molecule. I do believe they've also given the electronegative value, which is 4. Now, the most electronegative molecule is going to be, or the biggest difference from carbon, is going to give the most change in polarity. There's going to be the biggest change in polarity. So what we find here is that chloromethane and bromomethane, they're both methane. They've both got one part that is polar. Which of these has got a stronger electronegativity to give it a stronger polarity? Well, it's actually chlorine. Chlorine's 3.2, bromine is 3. Even if you didn't have these values, it's closer to fluorine because we know that's the most electronegative. Thus, the answer here is B and not C. This question was answered terribly because most people actually went with A or C. C and B were pretty close, but most people went with A. Weird question for people to go A with. It's most definitely B here. Chloromethane is easily the more polar of the two because of the electronegativity changes, and thus the answer here is B. As you can see there's my little explanation. All right, this one's from 2015. Now, with this question, I do have to note one thing. If I go to my data booklet, with the new data booklet, they've removed gold. Gold used to sit up, I think it was up here, in between chlorine and then like up here with your H2s. Gold was up the top. So all I'm saying is gold is somewhere around like 1.3, 1.5. It sits up here. So gold is all the way up here, just for context. So that's what you need for this question. So it says an electrolytic cell is set up to obtain pure copper from an impure piece of copper called a blister copper. Now, the electrolyte solution contains both copper sulfate and sulfuric acid. The blister copper on electrode 1 contains impurities of zinc, cobalt, silver, gold, nickel, and iron. The cell voltage is adjusted so only copper is deposited at electrode 2. Sludge, which contains some of the solid material impurities present in the blister copper, forms beneath electrode 1. The other impurities remain in solution as ions. The diagram is as below. The solid metal impurities that are found in the sludge are, which of those are found in the sludge? And then question 29, which of the following correctly shows both the equation for the reaction occurring at the cathode and the polarity of electrode 1? So have a go at this one here. For context, 48% of people got this one right, which for probably how straightforward this question is, isn't great. This question here, 31% of people got it right. This is a tougher question, so this makes a bit more sense, but only a third of the cohort got it right. So really good. So have a go at this one here, and note where gold is on the E-naught table. That will help you out. So 3, 2, 1, pause. And hopefully you're back. Hopefully you realized you needed the electrochemical series because I did tell you that. So it's really important, and you should have learned this by now, is that a blister copper or an impure copper has about 95 to like 98% copper. You should know that it's nearly all copper. Now, what that means is that as this copper is used up, everything that's left starts to fall off because there's nothing to attach to this electrode with, because the electrode is just folding away. But remember that it says there's zinc, cobalt, silver, gold, nickel, iron. So what is going to get used up first? So let's go down here and let's have a look. So we have a look at where our copper is. Where's our copper solid? And our copper solid is down here. And remembering that our strength is all based on going up on this side. And so therefore, what we're looking at is our strongest being here. Our strongest, so we're going down on this side. So our strongest is down the bottom and our weakest are at the top. So what's actually going to get used up first is anything below the copper. So anything below the copper is going to be some of your options here. So where's our nickel and where's our silver? Well, nickel's below it. So our nickel is going to actually get removed from this as an ion into this solution first. So the nickel is definitely going to come off. What else have we got? We've got our iron. So our iron is our Fe, which is down here. It's definitely going to get used up before our copper as well. So nickel and iron are definitely going to come off. Then we've also got cobalt. Cobalt is CO. Cobalt here is also going to get used up. So each of these are going to become ions before the copper starts to change. Then the copper starts to change, and anything that's left is just going to fall off. So what have we got left? Oh, we've also got zinc. Zinc. Zinc is also below. So zinc is also going to come off. So what am I left with? I'm just left with silver and gold. Now, if you scroll up, silver is up here. Gold is further up. It's actually not on here, but as I mentioned, it's further up. So given that this has nickel in it, so no. This has cobalt, nickel, iron, no. This is the only thing that's left. Silver and gold are the only things that are going to be falling off into the sludge. And then which of the following correctly shows both equations for the reaction occurring at the cathode and the polarity of electrode 1. So what we've got here is a bit of a different question in terms of what is the polarity of electrode 1 and then what is going on everywhere else. So in electrode 1, we know that copper here is becoming copper 2+. So if we go backwards, remember that oxidation involves loss. Loss here is loss of these. So this here is your anode. Now I know this is my anode. Now remember, this is electrolysis. We have a power supply. So being electrolysis, our normal way of thinking about our polarity or our positives and negatives flips. So this actually becomes positive because it's the anode and it's going through electrolysis or recharge if you want to think of it like that. So your answer is not B and it's not D. So you're left with not B and not C. I don't know why I said not D. Wrong one there. So you're left with A or D. So being left with A or D means you just need to figure out what is happening at the cathode. So I know this is the anode. This is actually the cathode. And at the cathode, I've literally been told in this question that the cell voltage adjusted that only copper is deposited at electrode 2. So knowing this is the cathode, copper must be getting deposited. So which one is the answer? Well, it's the one that copper is the product in, or solid copper. So the answer here is A. So the only answer here that you can get is A. All right, let's move on to some short answer questions. So we get a standard solution of sodium hydroxide, NaOH, must be kept in an airtight container. So this is from 2016. This is because NaOH is a strong base and absorbs acidic oxides such as carbon dioxide from the air and reacts with them. As a result, the concentration of NaOH is changed to an unknown extent. CO2 in the air reacts with water to form carbonic acid. This can react with NaOH to form sodium carbonic reaction, so sodium carbonate. Write a balanced overall equation for the reaction between CO2 and H2CO3 and water to form H2CO3. And write a balanced equation for the complete reaction of H2CO3 and NaOH to form NaCO3. So this is purely about writing out chemical equations. For some reason, people really struggle with this question. I think that the average mark on this question, I don't have it written down, but I think the average mark out of 2 was something like 0.4 or 0.5 out of 2 for obviously the 2 questions combined, which is not very good. So again, have a go at this question and then we will go through it. So 3, 2, 1, pause, and then let's go through it. So really important. You've been told what needs to go in here. So you're going to write CO2 and then you're going to write H2O. H2O. I'm not going to bother writing out everything that you need. I've got the answers on the next slide. And then that's all we know is going in. And then we have our answer here, which is H2CO3. Now, remarkably, given how straightforward this question is and how poorly answered it was, tell me whether this needs balancing. Tell me whether you need to do anything to this. I know you can't tell me, but think about it. 2 hydrogens. 1 carbon. 3 oxygens. 2 plus 1 oxygen. This question does not need balancing. There's literally needs nothing. You just need to know what are the right states. What people really struggle with in question was understanding this is aqueous. This here is aqueous. This is a liquid, this is a gas. We know that the CO2 is in the air and it reacts to form carbonic acid. And really important, we've been told it reacts with them. As a result, the concentration of NO is changed. It talks about how this is in the solution. It talks about this being in the solution. Thus, this has to be aqueous. Really important. You must have that down. And then in the next question, it asks you to say asks you to draw a chemical equation where these two react to form this. So in this one, you're actually going to have some byproducts. There's no hydrogen in here. There's no hydrogen. And you've got too many oxygens. When I've got too many oxygens and I've got too many hydrogens, what do I make? H2O. So you're essentially adding these two together to make this plus H2O. And you just needed to identify that and then balance. And as you can see here, these are the answers you get. People really, really struggled with this idea of the states in each of these questions. And it was the one thing that really held people back. And it's really something that's actually quite simple. So do spend your time identifying states and knowing how to go through with states. All right, continuing on. A 10 litre container is completely filled with a freshly made 0.1 molar NaOH solution. So this is still part of the same question. During chemistry class, 9.9 litres of the solution is used and the air enters the empty space above the remaining solution before the container is completely sealed off from the outside air. The container is then opened. Air enters the container at 101.3 kilopascals and 21.5 degrees. Assume the concentration of CO2 in the air is 0.04 volume to volume. Calculate the amount of CO2 in mole that entered the container. So this was something people really struggled with for some reason. And I think it was this here. So we'll discuss what's going on with this, don't worry. But please take a second and have a go. There are two different ways you can go through this question. So 3, 2, 1. Hopefully you have had a go. So the two different ways you could go through this is one, determine how much CO2 has entered via this. And then two, determine how much has entered via PV equals nRT and then use this. You do have to use, it's essentially the same thing. You're just doing one way and one the other. You do have to use both in both of them, but it just depends on which way you want to go about it. So the first method was to first find how much air has entered in terms of moles. So moles of air. Now, we don't know what's in the air, but we just know how many moles of whatever air is has entered. So essentially what we're saying is how much air is entered using PV equals nRT. We've been given all this information. We've been told this, we've been told that, we've been told that there's 9.9 liters and we know what 8.31 is. So we know each of our pieces of information. We know our degrees, which we changed to 294.5 because we're using kelvins. We know our pressure in kilopascals. We know our volume and we know our standard. We now know our moles. And then we're told at the end that assume that the concentration of CO2 in the air is 0.04. So what that means is that 0.04% of the air is CO2, which is actually as a decimal 0.0004, because that is a decimal version of it. It's like saying 4%. It's like saying 4%. Well, that's actually 0.04 as a decimal, or 40% is 0.4 as a decimal. This is 0.04%. So thus you need to change this. Now, what's really important in this question as well, there is significant figures. There are 3. There's 4 in this one, there's 3 in this one, there's 4 in this one, there's 3 in this one. You always go with the lesser. So there's 3 significant figures. They've made it so obvious there's significant figures in this question. You must use significant figures. If you do not use significant figures, you will not get the right answer. You will lose 1 mark. So you must use significant figures. So as you can see in this, we've done N of CO2, so we know what the moles are, and we know that it's 0.04%. So we've divided it by 100, which gives us this one here, and we've multiplied it by the 0.41 moles, and we end up with this many moles in our answer. Now that should be to the power of -4. I don't know why that hasn't gone as to the power 2. I do apologize for that. But in this case, it's 1.64, which is 3 decimal places by 10 to the -4 moles. Now, what's the other way you could go through it? Alternatively, you find how much of the volume is going to get taken up by the CO2. So you've got 9.9 liters. So how much of the volume is going to come up? So remember, again, you need to change this into decimals. So changing this into decimals, I go 0.04 divided by 100. Once I've done that and I've got my different decimals, I can go through and say, all right, this is 0.00396 liters. And I go through and I do this with 0.0396 liters. Instead of doing this beforehand with the 9.9, I've gone the opposite. I found the liters and I found my answer, again, to the power of -4. That one was put down properly. I do apologize for the last one. But that is essentially how you go through that question there. Hopefully that is okay. That is a difficult question in terms of this. You did go through this in Unit 1-2. This is distinctly a part of Unit 1-2. If you struggle with volume to volume changes, mass to mass changes, or parts per million, I do suggest having a look at your Year 11 notes, because it is something you do need to know, and it is something that you do need to be able to apply. All right, then let's look at the next part of this question. So the next part of this question reads that calculate the amount of NaOH in mole that would be present in the solution that remains in the container. Assume that the NaOH did not react with the CO2, and the container is shaken thoroughly, and you get all of this. Now, we don't have a lot of time left, so I will go through this very, very quickly. I'll probably just put the answers up and just very briefly discuss it. But again, I want you to pause, 3, 2, 1, pause, and hopefully you're back. So in the first part of this question, it's saying, look, calculate the amount of NaOH in mole that would be present in the solution. So again, we need to determine that the solution is only 0.1 liters of this. And then we need to talk about, all right, well, what is my concentration of NaOH? Well, remember that we've been told here the concentration is this, so we can go through and determine that we have 0.01 mole, and that's what we want to figure out in mole. Then it says, in the container is then thoroughly shaken, ensuring that all CO2 in the air is absorbed into the solution. Calculate the resulting concentration of NaOH in the solution. So you now have all of this information. Really important. You need to use all of the information that's here. You've got all of this information, use it. Apply it to your question. So now you need to know that you've shaken it all up, and there are 3 marks to this question. You need to figure out what are the moles reacting. So you need to figure out how many moles of what's going on. You then need to figure out what is remaining, and then what is the concentration of that. So I'm not going to go through this in super detail, again, just because we are a bit short on time, but this is the most important calculation because you are using this here. You need to make sure you come back and you use this here. You know how many moles of CO2, you then know how many moles of this, you can then do all of the rest, as you can see there. So let's continue on. This question here, let's go through this question here. Let's go through this part. So the average mark out of this was 3.5 out of 8. I'm going to very briefly go through it. So as you can see, submarines surface, they're using a PEM. A PEM is essentially a hydrogen gas, oxygen going in, and we get electrolysis and we get water as an output. Now it says state the function of the electrolyte in the cell, carry the current, you can say, or you can say moving of ions, pretty straightforward. Write the balanced redox equation for a PEM. Now this is something you need to know off the top of your head. You need to know it is H2 gas plus O2 gas goes to H2O. It's very easy to remember. Just remember it. Give 2 safety considerations. H2, very easy. So talk about ignition and its flammability. You can talk about the storage of it, all of those things. There's plenty of different points. This is what VCAR gave us. There's so many different points there. I want you to be able to go through that in a sort of pretty straightforward manner. Now, this is where it got more difficult. So it said state 2 advantages of a PEM cell compared to a diesel engine cell underwater. So I think probably the most important thing you want to talk about is that the most important thing you probably want to talk about is the outputs, because water being produced by a PEM cell, it can then be used in the submarine or it can just be pushed out of the submarine, because water is a very easy thing for a submarine to deal with given it is underwater. So I would say that is realistically the first thing you want to talk about. And I think the second thing is, again, talking about outputs. Think about the toxicity of diesel. Think about diesel as a fossil fuel. Think about particulates. I understand this is not combustion, but you're still going to get those things coming out. I'd say they're the two best answers. These are all the examples that VCAR gave. I find this one very interesting. I noted it because they're both essentially saying a diesel engine. Look, a diesel engine is combustion, but it's not really distinctly saying we're not using a fuel cell. So I think this one's interesting. I think you need to very delineate between the two and say a PEM is a fuel cell, whereas a diesel engine is actually combustion. And then you talk about you can then go on to talk about your particulates and the toxicity of the environment. But I think this is a really good one down here, talking about the outputs and how PEM is water. And it's actually quite a useful thing when you're underwater. So you can go from there. And then it says most submarines generate more H2 gas for the fuel cell when traveling on the surface. Explain how the H2 gas could be generated. So this was a very difficult question. And VCAR was very adamant at the end by saying, it's very nice if in this example here, you actually put some calculations. So it generates more H2 gas for their fuel cells when traveling on the surface. Explain how the H2 gas can be generated. Well, think about it. You're using a fuel cell to produce energy. Well, what's the opposite of redox in a fuel cell? Well, think about electrolysis. Think about reduction of water into H2 gas. Think about decomposition of water into H2 gas. This is probably the more common example. I probably wouldn't say decomposition is one that's going to come straight to your mind, and that's okay. But I think reduction of water, using redox, using electrolysis, find what water is, and you get more. Actually, put this in your answer. This is like using a diagram, which we talked about in our last lecture in June, July. Now what we're doing is we're actually talking about using a chemical equation. Use this chemical equation, put it in there. And then in here, as you can see, you get electrolysis of water and seawater using energy from the diesel engine or solar energy. So solar energy is probably a great answer in this one because you're thinking green chemistry. And as you can see, most students did not include both components of the response. A small number of students provided a method of generation and were awarded 1 mark. So really important, you need to explain both and you need to go through and probably give a chemical equation here. I think that is probably the best way to go about it. These were really tough VCAR questions. So we did actually get through all of them. We did blast through those last few. I do apologize. But as you can see here, these are tough VCAR questions. People struggle with these questions. If you are able to get comfortable with questions like that, you are going to sit ahead of the cohort and you're going to sit in a really nice place when it comes to getting your marks. So beyond that point, that is everything for today. I do hope that answered any questions you had. The chat will still be active in terms of you can read through the chat after this if you're at the premiere. If you didn't come to the premiere, you can see the chat. You won't be able to ask any questions in there, but hopefully the questions you had will be asked. Other than that, I hope you all have a great end of your year. Enjoy the end of year 12, and I hope the exam goes well. Other than that, good luck and thank you.